Hi everyone, we're continuing with 3.4 and 3.5. We're going to use the methods of the previous problems to solve real-world application problems. This is part C on exponential models. Okay, now one set of examples for exponential growth is population growth, the Malthusian population growth model. It looks a lot like the continuous compound interest formula. This over here looks a lot like the continuous compound interest formula. Now, this is a bit confusing because before, P was the principal, and it was over here. Now, P is the dependent variable. And instead of the principal P here, we have P naught, which is the initial population, the value of the population at time t equals 0, which is like a starting point. In my examples, I'll have time t equals 0 correspond to January 1st, 2000, although it might be something different. So we kind of have PERT, but the P here is the dependent variable. Population equals the initial population, P naught, a constant, times e to the RT. All right, so P is the population as a function of time t. P naught is a constant, the initial population, at time t equals 0. Remember, if t equals 0, this e to the 0 is 1, and we just get p equals 0. R is a parameter indicating population growth as a decimal. I'll have some comments about this in just a moment. I will say that if population is growing at 3% a year, we can basically say that R is about 0.03, but there is a discrepancy. I'll discuss that later. We assume t is measured in years. Okay. If R is negative, then we have a decay model. That means that population is shrinking. All right. So for example, and this is based on old data near 2000, close to 2000, example, use the Malthusian exponential model, P equals P naught e to the 0.0138 t to model a population of Earth, where t equals 0 corresponds to January 1st, 2000. Now the 0.0138 is telling us that we're assuming that the population of Earth is growing at a constant rate of about 1.38% a year. I'll discuss that later. Now, if the population of Earth on that date was about 6.083 billion, so our unit's going to be billions of people actually, in what year will the population reach 20 million based on this model? So we're asking, for what year will this happen? And it'll help a lot to find the value of t that will solve this equation when p is basically 20 billion. The unit is going to be billions of people. All right. Now, let's plug in. All right, so the initial population P naught is 6.083 billions of people times this exponential. And we want to know for what value of t will this whole thing equal 20 billions of people. Look at this. The billions of people unit will cancel out on both sides. We can divide both sides by the billions of people unit. So as long as these are in the same unit, even if it's billions of people, we can cancel those out. And we're basically down to that. There's an implication of this for finance I'll discuss in just a moment. Okay, now we're left with 20 equals 6.083 e to the 0.0138 t. And by the way, the fact that we're rounding off with the 6.083 billion, that may well overwhelm the fact that 0.0138 does not really mean exactly 1.38% growth per year. Okay, now we want to solve for t. Before we do that, it would help to isolate this basic exponential. And we can do that by dividing by the 6.083 on both sides. And as we're doing this, let's try to keep things as exact as possible. I know we're doing some rounding anyway, but let's try to keep our expressions as exact as possible so that we don't have to round off our calculator until the end. If we round off in the middle, we're in danger of losing even more accuracy. Okay, so we have this fraction equals e to this exponent, which contains t. Let's go ahead and switch sides. All right, and now the task is to bring this exponent down to earth. And what does a good job of bringing exponents down to earth? Logarithms. And so since we're dealing with base e over here, we may as well deal with the natural log. Let's apply the natural log to both sides. So we get ln of e to the 0.0138t equals ln of this fraction. Again, avoid rounding off too much in the middle. Let's try to keep this as exact as possible. All right, on the left side, what happens? We have ln of e to the star. Now, you could say that you could smack this down, and then ln of e is 1, but more directly, the natural log function and this base e exponential, these are inverse functions. They automatically undo each other. Do we want to say cancel? I don't like that so much, but for all practical purposes, you do end up with the exponent 0.0138t on the left side, either by the smackdown rule with ln of e equaling 1, or more directly by the inverse properties. Okay, so this here equals ln of this fraction, all right? To isolate t itself, to solve for t itself, divide both sides by 0.0138. I realize this looks ugly, but it helps to keep this as exact as possible so that we avoid losing accuracy. And we can approximate this on our calculator. Okay, be careful with grouping symbols. T turns out to be about 86.2 in years. So does that mean that in 86 AD, when the Roman Empire was powerful, that the population was 20 billion? No. Remember that T is the number of years since January 1st, 2000. So we add 86.2 years to January 1st, 2000. That means that we're somewhere in the year 2086. All right. Or sometime early in the year 2086. So based on this Malthusian model and our calculations, we claim that the population of Earth will reach 20 billion in the year 2086. All right, so let's take a look at this Malthusian model. This is Mathematica. Okay, so here's the graph of y equals that exponential function I showed you, 6.083 e to the 0.0138 t. It doesn't matter if software uses x. All right, so we get this j curve, right? It's an exponential growth function. We get this j curve. The initial value is this coefficient, 6.083. That's the time, that's the population at time t equals 0, January 1st, 2000. And we're saying that after about 86 more years, the population will be 20 billion, that red dot there. All right, now what does this Malthusian model predict for the year 2020? The prediction for 2020, if you plug in t equals 20, we get a bit over 8 billion. Now, what in fact is the population of Earth in the year 2020? All right, well, let's Google it. Population of Earth 2020. It's about 7.8 billion as of March 2020, about 7.8 billion. And we were approximating a bit over 8 billion. All right. Now, just out of curiosity, what's the population of the most populous country on Earth? The most populous country on Earth is China, which is over 1.4 billion people. Although, in a few years, China is going to be overtaken by another country, the country of India. And right now, India is it's just shy of 1.4 billion people. But based on growth rates, we believe that India will surpass China in a few years. This next one, well, let's do the United States. United States 331 million people and change. This one might surprise you. Indonesia. The population of Indonesia, over 273 million. Huge population. A lot of islands, densely populated. Okay, back to the main notes. On Desmos, by the way, if you graph this, you're going to have to really change your scales on your axes. Okay. Now, let's answer this particular question. Let's say we want to know when the population will double from about 6.08 billion to about 12.16 billion. How long will it take for the population to double from the population on January 1st, 2000? Well, there's a doubling time formula we can apply. So if you're dealing with a formula like this, and this applies to a continuous compound interest as well, by the way, the doubling time is given by t equals ln of 2 over r. In continuous compound interest, r is the decimal form of the nominal interest rate annually. I say nominal because that's what banks say per year, but in fact, it's going to be a little bit, there's going to be a difference between the nominal annual interest rate and the actual change per year. Again, I'll discuss this later. Now, this is independent of the initial population, and I'll show you what I mean by that. All right, so anyway, let's solve this in the case where the population we care about is twice the initial population. Okay, at what time t will the population p be twice the initial population? We'll replace p with 2p naught. Okay, 2p naught equals p naught e to the rt, and look what happens. This is why we have independence of the initial population. We can cancel the p naught on both sides. We can divide both sides by p naught. Of course, we're assuming that the initial population is not 0. Then there's no growth. All right, so we end up with 2 equals e to the rt. Much simpler. Let's switch sides. E to the rt equals 2. Now we want to solve for t. We want to solve for t. So for now, let's bring the rt, the exponent, down to earth. What will do that very nicely? Natural log. Let's take natural log of both sides. The natural log of e to the rt equals the natural log of 2. Natural log, base e, exponentiation. These functions undo each other. By the inverse properties, we have rt on the left. Or remember, you can smack down the rt, and ln of v is 1, leaving rt. We want to solve for t. We want to solve for t. And in order to do that, we divide both sides by r, which presumably is not 0. If r equals 0, you don't have growth. We need r to be positive to have growth. T equals ln of 2 over r in years. R as a decimal. Okay. Now, what this means, by the way, look at this. This is independent of p naught. What does this mean? Let's say we're talking continuous compound interest. Let's say that you and Bill Gates invest in the same bank, and you have the same constant annual interest rate, continuously compounded, where r is the nominal annual interest rate as a decimal. Again, I say nominal because you actually make a bit more after 1 year than r would suggest. Well, let's say that you invest $1 in this bank, and Bill Gates or Jeff Bezos invests $1 billion. How long will it take for your dollar to double to $2? And how long will it take Bill Gates or Jeff Bezos's $1 billion to double to $2 billion? It turns out to be the same amount of time. The time it takes both of your bank accounts to double is the same amount of time. The end results are different, 2 billion versus $2, but it's the same time to double, regardless of what the initial was. Okay. Now, in our Earth model we had before, R was approximated to be 0.0138 based on UN data near that time. So how long would it take for the population to double? So t is about ln of 2 over 0.0138. That's r as a decimal. That's about 52.2 years. So let's look at the Malthusian graph we had before. What we're saying is that in about the year 2050, we're going to double to about 12 billion people. And the graph here does seem to suggest that. All right. By the way, how long would it take to triple? The tripling time is given by ln of not 2, but ln of 3 over r. Basically, m is the multiplier you're interested in. If you trace back in the calculations, all right, if you replace p with 3 p naught for the tripling time, or 4 p naught, or m times p naught, look at the 2. That's where the m, the multiplier, would be. We would end up with ln of m over r in general. All right. Now, very quickly, this discrepancy between the nominal and effective growth rates per year. So in the formula p equals p naught e to the rt, the interpretation of r is awkward because we normally don't talk about the continuous compounding of people. So we might want to think about continuously compounded interest. Let's say we're told that population or your bank account is growing by 3% per year. This is called the effective yield. But when we're working with annual interest rates, you're usually given the nominal interest rate, maybe with various compounding schemes, let's say continuous. And the effective yield is going to be a bit different. So let's say that the effective yield is 3% per year. So let's say that, in fact, January 1st of one year, we see that the population is 3% more than January 1st of the previous year. And we assume that we have the same growth over time. Then K is 0.03. That represents the effective yield. So how is R, the number, the growth rate that you use in the formula, like PERT, how is R related to K? It's through this formula. R equals ln of 1 plus K, which people usually don't have to memorize in basic exams. Okay, so if you work out the calculations, all right, when K is 0.03, that means that the value used for R should be not quite 0.03, but 0.02956. But as long as K is small, usually these values are very close. And in a basic pre-calculus lecture, we don't freak out too much about the distinction between K and R. They tend to be very close anyway. Okay, so in a continuous compound interest problem, we would need a nominal annual interest rate of about 2.956% in order for our account to actually grow by an effective yield of 3% per year, January 1st to January 1st. Okay, if you solve for K in terms of R, you get this formula. Okay, so now we're going to talk about some other applications, and in fact, variations on this theme of population growth. So here's the thing. Do we really think that population is going to be like a J curve? Do we really think that population will grow like that? Well, a lot of people would say no. A lot of demographers would say, well, maybe there is a limiting factor. Maybe say 10 billion people, which is what scientists at the NSF said in the 1960s. Let's say instead that the limiting factor is 20 billion and we force a horizontal asymptote here. Then instead of a J curve, we could force this curve down and get more of an S curve. This is called a logistic curve. And that's an example of a logistic function, which involves exponential functions. It's an S curve. This here is called an inflection point, where the graph changes from concave up, like a J shape, where it's curving upward, to concave down, where it's curving downward. By the way, in coronavirus cases, that's what countries are hoping for first, that even though they might start with somewhat exponential growth, they're hoping for first an inflection point where the number of cases every day decreases. So here's where the number of new cases per day decreases. New cases, the number of new cases per day decreases. And then as people recover, If things get really good, then this curve can go down in terms of active coronavirus cases. But one value of the inflection point is that it's the point where we change from the rate of increase going from increasing to decreasing. Yes, we're still increasing here, but at a decreasing rate. Okay, here's another example of an S-curve, a logistic curve. So an S-curve formula looks more like that, and you see that exponential piece over here. L here, again, is the limiting factor corresponding to an HA, a horizontal asymptote. That's the long-run limiting behavior. We don't allow population, in fact, to touch or go beyond that. This is a simplified model. All right, so in a way, you could talk about population going through an India phase and a China phase. So again, the inflection point is the point at which the population changes from increasing at an increasing rate, the India phase, to increasing at a decreasing rate, maybe the China phase, especially during the one-child policy. That policy has since been altered. That point is called an inflection point. So once again, going back to this S-curve, it's kind of like this is the India phase where population is increasing at an increasing rate. The second derivative is positive. And over here, population is increasing at a decreasing rate where the second derivative is negative. The first derivative is always positive here. The function is always increasing. It's the sign of the second derivative that's changing in calculus from concave up to concave down for the original function. Epidemiology, when we were talking about coronavirus and the spread of diseases, that was this whole notion of J curves versus S curves. And we're hoping that it's more like an S curve than a J curve eventually. Also, the classic bell curves, the normal curves in statistics, this formula. This is the formula for a normal density curve for a normal probability density function with mean mu and standard deviation sigma. All right. So for example, let's say you have, well, the standard normal distribution has mean 0 and standard deviation 1. That's the horizontal distance from the mean line to either inflection point where you change concavity. Let's say you take a test where the mean is 50 points and the standard deviation, sigma, is 10 points. Here's a bell curve where the mean, the peak, is at 50 points. The standard deviation, the horizontal distance between the mean line and either inflection point, is 10 points. And here's a bell curve that models the performance of the class if the scores were roughly normally distributed. And there were many tests, like 1,000 tests in a big lecture hall. By the way, according to statistics, this means that for a normal distribution, about 68% of scores will lie within one standard deviation of the mean, between 40 and 60 points. About 95% of scores will lie within two standard deviations of the mean, between 30 points and 70 points, and about 99.7%, almost everyone, within three standard deviations, between 20 and 80 points. Some more applications. Newton's laws of heating and cooling. My grad school friend liked to call this the dead professor problem. Let's say that you're CSI and you enter a room and you see a dead professor on the floor, knife in the back. Let's say it's me. Okay, so let's say that I'm not really, let's say that I wasn't cold-blooded when I was alive, okay, and my body temperature was 98.2 degrees. That's the new estimate, I guess, 98.2 degrees, okay? Well, what's the deal? The idea is that you could estimate the time it's been since I've been dead by taking my current body temperature, all right? So it's like an inverse solve the equation problem where, for example, if my body is now 75 degrees Fahrenheit, how long has it been in hours since I was murdered or since I died? Okay, and again, this involves exponential functions. You can see a sort of exponential decay behavior over here. Likewise, there's Newton's law of heating. Let's say that we put, well, don't put me in a microwave, that's mean. Let's say we put soup in a microwave, where Here, this is the ambient temperature of the microwave. Likewise here, this was the ambient room temperature that I was in. That's the horizontal asymptote. Here, this is the ambient temperature in the microwave. The microwave is on. Okay. HA at y equals 100 degrees Fahrenheit. So let's say that the soup starts off here. You want to heat it up. Okay, that's Newton's law of heating. And again, it involves these exponential functions. Now, actually, in case you're curious how we get these kinds of functions, this is from Wikipedia. Here's Newton's law of cooling. This says that the derivative, the rate of change of temperature with respect to time, first of all, it's negative because the temperature is decreasing, negative slopes. That means the function, the graph's going down, right? We're talking about this guy over here, graph's going down. The rate of change of temperature with respect to time is proportional to the difference between my current body temperature and the ambient temperature in the environment, in the room. If you solve that differential equation, that's a Math 255 problem, you get this over here. The temperature of my body as a function of time is given by the temperature in the room, the ambient environmental temperature, plus the difference between my initial body temperature and the room temperature times this exponential. That's the solution of this differential equation. All right, so we've done a lot of solving of exponential equations. Now let's solve log equations. And by the way, we're going to need logarithms also. As we've seen, we've needed to use logarithms because if you ask questions like, for example, at what time did the professor pass away? Okay, if you go back to what time the professor passed away, again, given a body temperature, what's the value of T? How many hours has it been since the professor passed away? You're solving an equation. You're saying that equal to the body temperature, solving for X or T in this case, and you have to use logs for that. All right, so we're going to solve log equations next time.